as a non-trivial fraction of you know, I don't have a labor union card for the direct or indirect cascade labor union. And I haven't worked with Uriel, but I'm at Yale, and my closest faculty collaborator during the last 4.5 years has been Steve Warsaw. We teach classes together, taught classes together, wrote, failed, and some successful proposals together, and spearheaded a number of initiatives in the university, particularly in applied and computational math, one of which was, after 2 years, finally supported about 3 weeks before Steve passed. And during that time period, I got to know Uriel figuratively. He spoke of you very often and very fondly. And his ghost, Steve's ghost, is here. I've seen it a couple of times in the last week, and particularly that part of his being that thought so highly of you is certainly all around us here. I'm not going to talk about my work with Steve, which will be discussed in a symposium in his honor next year in Yale. I want to talk about something that has to do with our theme on the roundtable day before yesterday. So on form and growth, you'll notice, or many of you will notice that it's a juxtaposition of this title of a book that, I don't know, who's familiar with this book? Of course. Right. There's a controversy. I'm shutting this door because there's someone ringing in. The book wasn't very well accepted by biologists, and his motivation, Thompson's motivation for writing the book, had to do with the thought that biology was infusing too much evolution in the explanation of the forms that it saw. And he took the perspective that one should use physics, mechanics, mathematics to explain these natural forms that one finds in nature. And the problem is, of course, he really just did it by analogy. This looks like that. This looks like that. It was an amazing, it's an amazing compendium. It's over 1,000 pages of detailed observations in the tradition of a naturalist, where one sees something very robust and then sees something else very robust from the physical world and says these things are alike. But then the question is, how does the form relate to the growth, or vice versa? And this comes up in the context of just trying to understand physical objects, and it has a rather old history, some of which I will describe. And in that, we will address the issue of how do equilibria that we understand from statistical mechanics, and in particular, we always want to write down the equilibria so that we know where our solution is going to. Okay. But the question is, how is it when we view an object, its form, where are we relative to the equilibria? And that's the topic I want to walk through in a particular setting. So the value of equilibria. The problem in thinking about non-equilibrium shapes using equilibria, at least as far as I can tell, in the physical world, began with Thomas Harriot, who, for better or worse, was an employee of Sir Walter Raleigh, and he was tasked with finding out what the optimal geometry of stacking cannonballs was on ships. And he was a mathematician, he worked on this problem. He also later used the ideas of the packing efficiency, which now goes by the name of the Kepler conjecture, that the spheres, in fact, fill space most efficiently in FCC or HCP arrangements. Harriot then used this for early theories of atomism. And Kepler used it and was corresponding with Harriot in writing this paper on the six-cornered snowflake. So, so this idea of the geometry that emerges out of the constituents in equilibria is something that gave him grist. It advances the notion that an equilibrium concept is of some use in describing a crystal shape, in fact, a disequilibrium shape. Now there's an interesting further history of this that you may know of that has to do with another Thomas Hales, who was then at Michigan, and I think he's now moved to Carnegie Mellon. So Hales, in '98, produced a numerical proof of the conjecture, the Kelvin conjecture. It was controversial because he posited the proof by saying, if I minimize a function that has 150 variables, then I get this answer. Okay? They called this proof by exhaustion, literally. And it took years for the manuscript to be reviewed, and it was published here, and then there's an overview here. And there's a very nice book by Tommaso Esse and Dennis Weir that I recommend. Okay. So equilibria is, the idea of an equilibrium is really what underlied Kepler's argument for the six-sided snowflake.
You mean the Spaniards were packing their cannonballs differently from British at the time?
Of course.
This is where they lost.
I think they were just walking around with individual cannonballs. I don't know how they did it. Triangular boxes. So equilibrium crystals. So how does an equilibrium crystal represent its microscopic constituents? So we have a lot of ways to think about this. Generally, when we start dealing with an object and we ask what the role of the surface is, which is what we have to do when we think about a shape, the two-dimensional surface bound in a three-dimensional object, we think about the competition between bulk and surface terms. Right? So we'll add something extensive with area, and maybe there's an external field. And when we're thinking about liquids, that thing is a surface tension. And when we think about a solid, well, of course, it matters what the orientation of the surface is relative to the underlying crystalline structure. Right? So then the surface tension is replaced by a surface free energy, still obviously extensive with area in the same units, but it depends on the angle that you prepare the surface at. So it's the energy it takes to break the bond per unit area modulo the irreversible work, plus the energy it takes to torque the surface. Okay? And that gives you a surface stiffness, which is the sum of these two things. Okay. So this may be familiar to you.
This assumes small angles, or it works?
It's a general. So you're familiar with the fact that small objects have a lower melting temperature, right? So a metastable equilibrium of a small solid in contact with its melt is shifted from the bulk phase diagram by delta mu. Okay, in bulk coexistence, right, it's arbitrarily large, and so this goes to 0, delta mu goes to 0. Okay, and so there's the invariant as you move around the surface is that delta mu has to be fixed. So the geometry, the product of the surface stiffness, as you move around the surface, increases, the curvature must decrease. Okay, that gives you the underlying structure, but it doesn't. That, if you will, is a boundary condition that has to be satisfied on the surface. So to understand the shape, there's something called the Wolf construction. I just put there's beautiful pictures. The group in Marseille, this is pretty much what they've done for years. Absolutely fantastic work. The question still is, it's a UHV system. They prepare lead and they wait. And they wait, right? They wait. And they say, well, it doesn't change. Is it in equilibrium?
What is the melting temperature?
600 degrees. All right, so in 1901, Wolf first described the notion, which I'm interpreting now in a slightly different way, that an equilibrium crystal shape is something that minimizes the total surface energy for a fixed volume. Okay, so the Lagrange parameter is a fixed volume, so it minimizes this integral. But it proceeds in the following way. If God or some close associate walks up to you in the street and says, okay, lead, I'll give you the surface energy as a function of all possible orientations. Here it is. Okay? Well then, right, then you just have to minimize this integral and you give me the shape. Okay? But, God is never that friendly. So normally what people do is to wait until the thing reaches an equilibrium and try to invert this to get the surface energy, because you'd like to know that. So here's what the shape actually is. You want to imagine that since God gave you the free energy, you make a polar plot of that, okay? And then you want to take an inner envelope, which is just written as a set of all points such that the projection of a radial on the normal, okay, is bounded from above, okay? And so that's this inner envelope, and you just see the geometry of it as I constructed it here, and so that's the Wolf shape, okay? Now it turns out that Wolf's paper, his study was actually motivated by wanting to understand crystal growth. Okay, so he has here now a global thermodynamic equilibrium statement, which is that something that's minimizing its total surface energy is what's giving me the growth form. Okay, that's what he was doing. We all now view this as the equilibrium description. Okay, now sometime later, and this makes a contact with what I'll talk about in a minute, Charles Frank and Alex Chernoff sort of independently came up with the idea, which is that if God or some close associate gives you the velocity of the normal everywhere, then the steady state shape is determined in exactly the same way. Okay? Now this is of interest because this result, which is useful both by intuition and cosmetics, is actually dangerous because it doesn't tell you anything about initial data. And if your initial data are not convex, then we can have a reconstruction problem.
Yeah.
Okay. Right?
And
We have a series.
velocity plays a role of energy effect.
Exactly. Yeah.
But it could be not one-to-one.
Yeah. So we'll get finite time singularities. We'll get shocks. So I'll come back to that.
But I mean, this principle presumably doesn't have the sanctity of the one above. I mean, this is just an ansatz, is it?
That's right. That's right, and that's right. Well, you can derive that it's reasonable by having a kinetic model of how the surface moves, which is what I'll come to before lunch, hopefully. So Kepler took us in one direction, and not that much later, Descartes, in the winter of 1635, was in Amsterdam, and he was looking at snow, and these are pictures from his studies, which appeared in a fairly well-known document, which is argued to have launched the scientific method. This is reproduced in an article by Sir Charles Frank of the Frank-Chernoff construction. And he immediately thought of these things having nothing to do with equilibrium at all. But he was amazed, and these are just excerpts from his notes, and that, how could nature do this, make something so regular, particularly when the environment in which this thing is living, which we were seeing the day before yesterday, I guess, about non-spherical shapes, is so violent. So how does this happen? Of course, that's one reason that we know a lot about the kinetics of crystal growth, because people would like to control the shape of an object. Okay, under very well-defined conditions, you want to know how you can reproduce various parts of a diagram of a single material. Okay, so there are a lot of natural questions if you're interested in this kind of a reconstruction problem. Okay. I think it's important to realize that both in experiments and when you observe something in the natural environment, really most things are not in equilibrium. So a rock, it doesn't change on the time scale of your life, but it was violently hiccuped out of the earth, laid on the ground, and it's not in equilibrium. It's just that it's been isolated from the opportunity to equilibrate on a reasonable time scale. It just takes a heck of a long time. we just like to understand these things for aesthetic reasons and what controls them. When are aspects of equilibria necessary, and when are they necessary and sufficient? And can we understand things that are relevant to everything? Okay. So now, because the tigers were so interesting, I'm going to pay the price. So I'm going to go very quickly and gingerly through some critical phenomenon by pictures. Okay. So there's relevant equilibrium and disequilibrium transitions to understanding the crystal growth problem. Okay. Two of them, surface roughening, surface melting. One of them is called kinetic roughening, and there's one that I invented, which I'm not going to talk about. Okay, there are two types of orientations that coexist on a surface, or can coexist on a surface. One is molecularly smooth, one is molecularly rough. So you can just think about it exactly like this picture. If you walk along the surface taking steps slightly larger than a lattice parameter, then you have a molecularly smooth surface. And here's a hill and valley structure on the scale of a lattice parameter. Okay, so on a single crystal, like you saw in this wolf shapes, I can have these things coexisting. Smooth and rough orientation. Moreover, I can take one of these and make them into one of these, and that's a critical phenomenon. Okay? That's the roughening transition. So the idea there is that I raise the temperature. See, at absolute zero, I had to do a lot of work against the enthalpy of fusion to put this atom on the surface, right? But I get very little from entropy and configuration. As the temperature rises, entropy wins, and the surface disorders, and a facet can become rough. So that's just the equilibrium state of the surface. Now it's important in thinking about that, both in equilibrium, what it does to change the underlying surface free energy and the surface stiffness, and therefore the shape, but it's also really important to think about what happens to a molecule or atom when it hits these two different types of surfaces. Okay. So helium-4 is the test bed because you don't have to wait. Okay. If you don't know why, we can talk about it later. But you see, the crystal becomes much more polygonal as the temperature gets lower. Ice does it. This is looking down the c-axis of a single crystal of ice. And so this is the familiar hexagonal structure. These are literally facets. They're called the prism facet. And as you go, see above this temperature, you see at minus 16 degrees, 160 megapascals, this is ice and water, then this facet undergoes a roughening. Okay. So another one that's relevant is called surface melting. It's also a critical phenomenon. And it's a special case of triple point wetting. And the idea here is that if you imagine preparing a solid vapor interface, okay, so you cleave an infinite solid, you throw away half, you bring the remaining in contact with the vapor at coexistence along the sublimation line, and then you walk towards the triple point from below. And then when you get near the triple point, you will see a thin film of this material disjoining it from its vapor. Okay? Water at the interface between, say, solid and vapor. And that will grow as you approach the melting temperature from below. And this is observed in metals, rare gas solids, molecular solids, including ice, quantum solids, and so forth. Here's lead melting at 600 degrees, looked at by ion backscattering, a number of molten layers diverging. This is Michael Elbaum's thesis on ice. That's 0 degrees. You see hundreds of angstroms of water at the interface between ice and the vapor. Okay, so ice. So when you step on ice, it's slippery, near zero, but below zero because you're stepping on water. It's better when it's cold. Right? All right, it's a critical phenomenon. It has an amplitude and an exponent that's tied to the melting temperature. Okay. And 5 minutes. 5 minutes. Tigers. Right. Disequilibrium transitions. Imagine I have a facet and I want to grow it normal to itself. Okay? Well, one atom doesn't do a job. I have to get a bunch. So I have a nucleation problem in lower dimensions. So I have a line-to-surface barrier to creating this two-dimensional nucleus on the surface. And it suggests an interesting problem of arrested equilibrium. That is, I can have a finite delta mu but a non-moving surface, right? Because I can't overcome the nucleation barrier of this pillbox on the surface. But I can increase the growth drive. I add to this boundary, it creates a monolayer. As I continue to increase it, I can get multiple monolayers, okay, filling up, or multiple islands filling up a monolayer. And if I go above a critical value, it will roughen because the underlying material is buried. So we've heard KPZ and so forth. All right. So now, how does this work? Here's an experiment of an axisymmetric, nearly two-dimensional system of CCl4 growing from its melt phase. And this is just the upper right-hand quadrant. You have, say, all orientations on the surface between 0 and pi over 2. So it's a continuous surface curvature there. And you grow it. And what you see, of course, is that these hardly move because there's activated growth parallel to the facets. And the rough orientations grow out of existence, okay, leaving the system fully faceted. And so a target for theory is to say, well, look, there's two ways I can go from this state that has all orientations between 0 and pi over 2, and this that only has 0 and pi over 2. Okay? One is that I can have a continuous increase in curvature until I add the last atom. And the other is that I can have regions that increase in curvature and regions that decrease in curvature. Okay? And those are associated with where I get discontinuities in the surface slope. Okay, so how do we understand that? We model the surface as a string, okay? You know, a real string that's highly constrained by the underlying crystallography. And all of the physics, so I had a 2 vector that defines the surface, there's a normal and a tangent. All the physics is in here, so that's the ansatz, okay? But the ansatz I can build up from experiment and build up from the statistical mechanics of the stuff I've been talking about, okay? And so I want to evolve this string, and it's called geometric because while diffusion is responsible for material coming from the bulk to the solid, it's not what controls the shape of the surface. What controls the shape of the surface is the structure of the surface, okay? Its orientation. Okay. All right, so I can have anisotropic growth, right? I have 6 facets and 6 rough regions, okay? Fast growth, slow growth. Okay. That controls, if you will, that's the underlying molecular constituents, and these are the kinetics as you move around. That's the ansatz. And you can see, depending on, so you know that I can solve this equation by characteristics, right? And so the characteristics are straight lines with trajectories, and the magnitude of the trajectory depends on the physics underlying the kinetics of the crystal growth. And you can imagine then that surface orientations, which are fast, could collide, okay, competing for orientations on the surface, and these shocks create a discontinuity in the curvature, okay? And so that gives you an underlying edifice to study these corners that move, okay? These were, in Mogan's talk yesterday, had grain boundaries, okay? It's the same idea.
So where's temperature in your parametrization of this problem?
There's no temperature, okay, except for in the growth drive. So the delta mu on KT is the actual chemical potential difference between a molecule in the bulk and a molecule on the surface. Right, so now I have like a minute. Ice and water. Let's look at this. Okay. So I want to ask what happens when this melts. Okay, so I'm going to melt it. And the most reasonable place to lose material is at the corners where there are the least number of bonds. And so these are going to start to erode away the corner, and you lose the facet. And you see higher order structures here. Okay, it actually becomes 12-sided. But now look at this orientation. This is an A-axis. As you come to this point, it looks like the A-axis has rotated by 30 degrees. Okay. So if someone walks up to you on the street, gives you this crystal, says it's ice in coexistence with water, gives you this crystal, what does the shape tell you about its equilibrium? Okay. So you need more information. You need its history. So, and of course, as you grow that shape, it's re-entered to the shape that you began with. Okay. So now, let me just step through some examples very quickly. If I do the same experiment by putting in a a biopolymer called antifreeze glycoprotein. They exist in nature. They keep all sorts of organisms from dying. Okay? And I do the same experiment. Ido Broslovsky does. Melting, growing. I get this rotation. Okay? But importantly, this is 20 or so degrees above where we were for the pure case. Okay? So nature, biology somehow knows what orientations are fast, what orientations are slow. Where should I adsorb onto the surface, okay, and change the growth? So it shifts the roughening transition by 20 degrees so it doesn't lead to explosive growth in the organism. So we know what it's doing, and we're still working on trying to understand why. In 3 dimensions, it becomes more interesting. The problem of snowflakes is an old problem. Okay, so the simplest example you could come up with, this is growth rate, and this is temperature. What's been observed now, this is called the Nikkei diagram, is that you get transitions from plates to prisms to plates to prisms. So that is, the thing grows like a pancake, then like a wand, then like a pancake, then like a wand. The transitions are within a tenth of a degree. Okay? We don't understand that. It involves a confluence of these phenomena I've been talking about, but we can't actually predict where they occur. It's the simplest problem in the book. We don't understand it. We heard a little bit about thunderstorms. It turns out that to get the charge separation in a thunderstorm, you have to deal with collisions between particles moving up, particles moving down. And so this issue of knowing how particles move that are non-spherical in a turbulent flow is relevant. And finally, just say that many of you know that we live in a solar system, and the time of the evolution of a solar system comes through a collapse process, creating a accretion disk. And eventually, the sun evolves, creates a photoevaporative wind, and starts to sweep the disk of the material that one needs to form the planets. And so one needs to form planets on a time scale that's fast relative to a few million years, otherwise you get rid of the stuff you need for the planets. And this involves collisions between particles in an accretion disk, and these kinds of processes that I've discussed are underlying that. So, as a whirlwind tour, I hope give you some appreciation that there are some interesting aspects of this reconstruction problem that force us to think about some basic issues. The idea that I wanted to really emphasize is that you have to be very careful when you see a form and ask yourself whether it emerges from thinking about equilibrium concepts or strictly disequilibrium concepts and how they're linked. And if you follow your nose a little bit, you'll find out that there's a lot of implications to some of these issues. This is a long list of collaborators. It was John Kahn who originally got me interested in geometric crystal growth, and Greg Dash, who's now recently left us as well. So I want to thank them. And thank you, Uriel, for bringing us all to this Hilton hotel, which for all of us at different ages, if you weren't at dinner last night, you don't know what this means. We all have different reasons for being here.